So in displacement, the viscous forces are important. They are a pressure drop as a driving force and fluid viscosity as a resistance. But there are other forces which play a role, namely capillary forces and gravity forces. Capillary forces tend to try to increase the saturation in the direction of lower saturation. And in this experiment you can see water trying to imbibe into this porous medium, the capillary forces creating an increasing saturation of water. But it is a slow process, as you can see. When a single fluid tries to flow through a pore space, it enjoys the whole space, which defines the so-called absolute permeability. But when two fluids try to share the same space, their individual permeability is reduced to the relative permeability, a fraction of the absolute, and a function of the saturation of the fluids. We can measure relative permeability on core plugs. If we then divide the relative permeability of the fluid by the fluid viscosity, that gives us the mobility of that fluid. If the mobility of water is greater than the mobility of the oil, we're likely to get unstable displacement. The gravity forces segregate the fluids according to their density, and this is a stronger force when the reservoir is vertical like this as opposed to slanted, where the gravity forces will have less effect. So if we're water flooding a light oil, we're likely to have a mobility ratio less than 1, which is favourable, and regardless of the rate we displace at, we will get a stable displacement with gravity forces being strong. With a viscous oil, however, we'll have a mobility ratio greater than 1, unfavourable, and we're likely to get underrunning of water unless we've displaced at a very slow rate, in which case we could establish stable displacement, but this would have to be done very slowly. So if this stunning outcrop in front of us was an oil field full of heavy oil and we were trying to water flood it with, let's say, a water injector at the lighthouse at one end of the outcrop and an oil producer at the other end of the outcrop about 1 kilometre away, if we tried to achieve stable displacement, we'd have to produce so slowly that it would take about 1,000 years to recover the oil. Even if we put the producers and injectors 100 metres apart and tried to achieve stable displacement, again this would take about 100 years. These are clearly non-commercial timeframes. So we have to accept really that to get to commercial development, we'd have to displace at unstable displacements and live with a lot of water production during the life of production of the oil. Now our facilities engineers would need to know this because they're going to have to design the plant to handle high water cuts throughout the field life. How do we make these predictions? We use fine-scale reservoir models with plenty of vertical resolution to model the balance of viscous and gravity effects. In this way we can try to find the balance between an ideal physical displacement which takes potentially too long and a rate which is commercially acceptable, albeit with high water cuts. Water flooding? Yes, but it's not just what you do, it's the way that you do it.